I got everything. I will begin with a word of prayer. Heavenly Father, we thank you for this time we have just to meet and study your creation. Thank you for this class. Just ask that you just guide our steps today, help us to understand a little bit more about advanced calculus. And again, we just thank you for your many blessings, Lord. In your name I pray, Lord Jesus. Amen. So I'll read you a quote from page 56 in my 2015 notes. We're getting into the section on partial derivatives in the Jacobian matrix. And here's what I say. I said in the preceding section, we calculated the differential at a point by educated guessing, but we'd like to find a better method to derive differentials. Turns out we can systematically calculate the differential from partial derivatives of the component functions. However, certain topological conditions are required for us to properly paste together the partial derivatives of the component functions. That's a story we'll be telling not just today. I probably won't even get to that theorem today. But ultimately we need continuous differentiability of the partial derivatives in order to put them together to get differentiability. But you know, one of the things that's sort of dogging us conceptually from the start of this is like you're given a mapping from a vector space to another vector space, and then, you know, part of us wants it to be the case that the derivative is again a mapping. Shouldn't the derivative of a mapping be a mapping? Well, actually no. So what is the derivative? What describes the change in a multivariate function essentially is not just the same kind of multivariate function. It's more complicated than that. And Dudney said it best, I think, in his chapter on modern analysis, chapter 8. Here's a quote from him. The subject matter of this chapter is nothing else but the elementary theorems of calculus, which, however, are presented in a way which will probably be new to most students. That presentation, which throughout adheres strictly to the general quote-unquote geometric outlook on analysis, aims at keeping as close as possible to the fundamental idea of calculus, namely that the quote-unquote local approximation of functions by linear functions. In the teaching of calculus, in the classical teaching of calculus rather, the idea is immediately obscured by the accidental fact that on a one-dimensional vector space there's a one-to-one correspondence between linear forms and numbers, and therefore the derivative at a point is defined as a number instead of a linear form. This slavish subservience to the shibboleth of numerical interpretation at any cost becomes much worse when dealing with functions of several variables. So I love this quote. And then Dudney spends the next half page continuing this thought with explicit examples of how our custom of calculus presentation injures the conceptual generalization. In other words, the way we teach Calculus 1 is foolish if we're really trying to build intuition for what the derivative is in general. It is acting against that purpose. So we have a lot, in some sense, to sort of conceptually unlearn. The big idea is just that the derivative is really the best linear approximation to the change in a function at a point. And if your function is from R to R, well, a number suffices to describe the best linear approximation to the change because it's just slope, basically. But if you're defining the best linear approximation to the change of a function of 2 or 3 variables, you can't just give a slope. It's more complicated. Yeah. So anyway. So we should talk about, I think last time I proved that a linear function is continuous, right? So I guess I'll start with an example. If I have T, a linear transformation from vector space V to vector space W, right? Then the differential at any point to T is just equal to T again. So what's the best linear approximation to a linear map? Well, guess what? Itself. And to prove this, well, just look at, T of, let's say, P plus H minus, T of P. Well, what's that equal to? Well, that's equal to T of P plus T of H, right? minus t of p, which is equal to t of h, right? So if we set, the differential of p of t is equal to t, then you can easily see that t of p plus h minus t of p minus the differential of p at t of h is just identically equal to 0. So we don't even need to quantify the error function like the eta we talked about last time, and it's just 0. There's the Fauché quotient follows for free. Great. So what could be more simple than that? So that implies that, of course, the limit. Well, let me not even write it down. So t is differentiable at p with the differential, just the mapping itself. So that's one thing. I sometimes forget to mention this, but it should be mentioned, right? Another thing you could easily prove is that the differential of a constant function is 0, right? If I have, I won't even write out the details, but if I had, f of x equals to w naught for all x in vector space V, right, where w naught is a fixed element of the vector space W, then for f defined from the vector space V to, and by the way, I don't have to have f defined from V, right? I could say for all x in S, right, where S is like some subset of V, right? Certainly I could do that. So this from this to W has the differential of f at p just equal to the 0. It's differential 0. But to be fussy, it's what is it? It's the mapping. It's a linear transformation that maps the 0 in V to the 0 in W. I am assuming that S is a subspace of some normed linear space V, as our usual rule goes. Okay. All right. So then, I'll get back to the partial differentiation thing, but it occurs to me I have a few more geometric theorems. So I would say a geometric theorem is one which doesn't, at least the result of the theorem doesn't rely on our choice of basis. It's something that can be set at the level of like linear transformations in vector spaces. One of those theorems that we could state, excuse me, is this. Well, let's suppose, I won't even prove this one, okay? But if we had f from, let's say, from V to W, right? And if we have G to W, right? And if P is an element of the intersection of their domains, such that F and G both differentiable in the Fauché sense, of course, at P and V, then guess what? The differential at P of F plus G is equal to the differential of P of F plus the differential at P of G. Well, maybe I should prove it. I don't know. But the proof goes something like, oh, fine, let me prove it. Let me prove it. I will use the technology that we introduced last time to make the proof easy, right? So what did we have last time? We introduced the error function, right? So like differentiability at P means that we can write f of P plus H as equal to f of P plus the differential at P of F times H plus the error function eta. Let me put a sub f on it since it's attached to f here of H, right? And likewise, G of P plus H is G of P plus the differential P of F, of G rather, right? Of H plus the error function in G at H. And then if I add these, what happens? I get f plus g of p plus h, right, is equal to f plus g of p plus the differential of p of f plus the differential at p of g of h, right, plus a to f of h plus a to g of h. Now, by the theorem I stated last class, right, that's almost everything I need for differentiability of the sum. Right, the full statement of this theorem is that, well, the sum of two differentiable functions is once more differentiable, right? And not just that, the derivative is, in fact, the differential is the sum of the differentials. The differential of the sum is the sum of the differentials. So this formula is almost everything I need, but what do I need? I need that, I do need to verify that this right here satisfies the needed condition to capture differentiability, right? So this is almost everything. I need this identity, but I also need that the limit, right, as h goes to 0 of what? A to f of h plus a to g of h divided by norm of h, if I recall correctly. That has to be equal to 0, right? But that is equal to 0 because we're given that the quotient of the error function for f and the error function for f separately are equal to 0. So by linearity, the limit. And so incidentally, there's another way to prove this, which is kind of more from direct combat with the Fouché differential. I mean the Fouché derivative definition of limit. And so I think if you go through that, if you really think about what you're doing, if you go back to the definition here, what you'll find is you're really reproving the limit law, because you'll end up like taking the minimum of the two deltas to get the epsilon over 2 for both. It's like I've done that in the past, I'm pretty sure, to prove that the sum of differentiable functions is differentiable. Like, you know, I pick a delta and I can pick in two deltas, one for f, one for g. The one makes the, you know, Fouché derivative, Fouché quotient for f behave. The other one makes the Fouché quotient for g behave, and so you get the Fouché quotient for f plus g to behave. But I think this is a better way of arguing, because we've already proved the limit law, we might as well use it. And so this is separately 0 and 0. The reason I can break the limit up, of course, is that both of those separately exist and are 0. Consequently, the sum of the sum of two differentiable functions is differentiable, and the differential is the sum of the differentials. Okay, that's not too hard, right? And you can pretty easily see that we can soup up this argument and pull constants out, right? Like, if I just throw some c's in here, right? Like put a c, I don't know, where do you want to put it? On the f or the g? I'll put it on the, I'm going to fit it in here to the f. C, right? That puts a c here. So c, 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 c. I guess it's just C here. C pulls out probably. Something like that. All right, but anyway, I don't want to. Okay, so let's see, let's think about basic calculus. We've got differentiable implies continuous, we prove that. We've got that the derivative of a sum is the sum of the derivatives, that the derivative of a linear function is a linear function again, derivative of a constant 0. What else is there? There's the product rule, quotient rule, but first we're going to do chain rule. So what would the setup for the chain rule look like here? By the way, these things aren't in my notes because I'm trying to stay at the vector space level longer for this class than I have ever before. Because I've always like shifted over to finite dimensional vector spaces. I've shifted over to Rn in previous times to make the students less annoyed. But we can do it. Okay, so I want to compose two functions, so I really want to think about f. And just to keep things simple, I'm going to, oh fine, domain of F, right, subset of V, which goes to, let's say, W, and then G is a mapping from the range, well, let's say the domain of G, it has to be a subset of the range of F, right? For this to make sense, which of course is a subset of W. And let's suppose that that maps to, where's G mapping to? I got V, I got W. Let's make U the target space of G. That's where it's going to. And we're going to suppose F is differentiable at P and G differentiable at F of P. All right. What do you, so what's the chain rule going to say?
The differential of F compose G at P equals the differential of F at G of P.
Right, at G of P, composed with the differential of...
That's it.
Oh man, I did it wrong. Look, I'm a dummy. I'm a dummy. All right, let's think about this. If V goes to W, and then, so the way I've arranged things here, we need to talk about the differential at P of G composed with F. That's what we should be looking at, right? Because F goes from V to W, and then G goes from W to U. So that's, I always do this. But anyway, it doesn't matter, letters, which come first, G or F, whatever. So that's what we have. And you're saying that this is the differential at F of P, right?
Yeah.
Of G, composed with the differential at P of F. That is, in fact, the coordinate-free chain rule right there. It's a statement about the composition of linear maps. And to prove this, we can again use the Carr-Theodori type argument that we introduced last time. That makes for an easy proof here. See, because so we have on the one hand, we have that F of P plus H, right, is equal to F of P plus the differential at P of F times H, right? Plus eta sub F of H. We have that, where the error term, the eta sub F term, vanishes upon division by the norm, or by itself, okay? And we also have G of F of P. Now G is a little bit trickier because it's differential at F of P. So we, G of F of P, right? And let's use a K here, or some other letter maybe. I'll make my K look really, I don't want to use K. Let's see, fine, K. So I'll use a very funny looking K. That K, okay? I want to make sure my K doesn't look like my H, that's all I'm saying. And that, by differentiability of G at F of P, is G of F of P plus the differential at F of P of G acting on K, right? Plus what? Plus eta sub G of K, right? But then we can look at G composed with F of P plus H. What happens then? Well, by definition, that is g of f of p plus h, right? Which then is, so we can come up to here and do that, right? So that's g of f of p plus dpf of h plus the error term. However, let's see here, then I want to think about all of this right here being k. And then I do this, right? I get myself g of f of p plus the differential at f of p of g of the differential at p of f of h plus eta sub f of h. All right? And then plus eta sub g of the differential at p of f of h plus eta sub f of h, right? Now, then what? Well, the differential is linear, right? So to start with, we have g of f of p plus the differential of f of p at g of the differential at p of f of h plus the differential at f of p of g of the differential of eta sub f of h, right? And then plus eta sub g of the differential at p of f of h plus eta sub f of h. So let's think about all this. What do we need to prove? We need to prove that there exists an eta sub, g composed with f, right? Such that if we look at g composed with f of p plus h, we've got g composed with f of p, right? Plus the differential of g composed with f at p of h, right? Plus this eta sub g composed with f of h, right? where this is linear, right? And this needs to have the limit as h goes to 0 of this thing. Being 0, right? So it's pretty obvious that this piece right here, we can, so this is going to be the differential at, f of, differential at p of g composed with f, right? Acting on h. We can claim that should be that. It's linear because it's the composition of linear maps, and we know from linear algebra that when you can compose linear transformations, you get a linear transformation. So that's linear. Yay. So then it stands to reason that all of this stuff over here, all this jazz, should be what we call the error function for the composite. I'm not sure that's quite... Oh, okay, so then all we got to do is take the limit as we, divide this by norm h and look at its limit, right? And I think we can treat the terms separately. So like, for example, d f of p g eta sub f of h, right, divided by norm of h limit. Well, think about this. This we proved is a continuous. We proved that a linear map is continuous, right? That means that I can pass the limit inside the map by the composite, like the chain rule for limits, which admittedly I don't guess I proved in here, but we could prove that in like the same way you do in topology of metric spaces. But anyway, so the point is they got d sub f of p of g of the limit as h goes to 0. This is by continuity of the differential. Since it's a linear map, I can pass the limit inside. All right. And then, well, this is by assumption 0. And then we're feeding 0 literally into a linear map, which is then 0. So that piece goes to 0 upon division by h. And something similar happens for this. I'll do that in a different color. What I'm doing right now is definitely an improvement of what I have in the notes. Okay, but because what I have in the notes is written by hand, and I think it's a sketch. It's not quite a. This is probably a proof. I don't think I'm skipping anything really. Eta sub g of dpf of h. Ignoring the gap, of course, that I haven't proved the chain rule explicitly in here, but you could do that. I mean, not the chain rule, the composite limit rules, the thing I haven't proved. All right. How do we do that limit? Well, this is supposed to close here. So again, I guess I do need to, Well, maybe to be picky here, I'd need to be more picky, but let me explain why this limit's 0. So if you look at, I mean, this could be made rigorous, all right? This right here, let's call, I need something. Let me call it alpha. Call that thing alpha of h. What happens to alpha of h here? Well, as h goes to 0, you've got what?
The error goes to 0.
Right, so that
Goes to
that exactly limit of a, we're taking as h goes to 0, this is going to 0, and this is also going to 0, so it's all going to 0, right? So I could replace this essentially with the limit as alpha goes to 0.
But doesn't the differential at b goes to
Of eta sub g, just a second, of alpha, hold that thought, of this, right, which is 0.
the differential of b? The differential of f at b as h approaches
Yeah.
0 goes up. Okay, nice.
By continuity of the linear map, which is 0. But we also know that this goes to 0. So if I make a substitution, if I call all of this alpha, well then alpha is going to 0, right? So I think that's, I mean, this is a little bit of a cheat, but I mean, I think this could be made rigorous. Admittedly, there's a little bit of a jump here. So anyway. So there you have it. That is the chain rule. Is good?
Yeah.
Okay, cool. Now, the product rule, I just prefer to look at the product rule in a less geometric way. I don't know, like product rule probably, I'm not, this is, now that I'm asking the question, I'm just not sure if I can do the product rule at this level of like abstraction. The question is, what kind of product am I talking about? You know? Yeah. Well, for an R3, we could do cross product, yeah. What if I try to do like that general product I introduced? Do you remember what I said? It was like, what was my general product? I think I called it star. It was a mapping from, what was it? W1, was it W1? I think I used W1 cross W2, and I let it be W3 valued, wasn't that it?
Yeah. I'm in the Cartesian product, not the cross product. If we take the Cartesian product being like domain F and domain G.
Oh. Oh, well, if we're talking about Cartesian product of F and G, then well, goodness, I'll have to think about that. My mind's drawn a blank at the moment. Would this general product, would Cartesian product, I mean, the rule for this was what? We had, for example, like x1 plus, you know, y1 star x2. What it was x1 star x2 plus y1 star y2, right? And we can pull constants out as well. And likewise for the, it's bilinear, right? Yeah. So at the level of functions, so we would want to look at, we would want to consider like F1 a mapping from, you know, some subset. Oh, let me not use U.
That's an X2 at the end.
Oh, thank you. Yeah. Yeah, you see it. I don't see it. I'm too close to it. So F1 is from, you know, say the domain of F1, a subset of V, and we'll let it be W1 valued. We could let F2 be from the domain of F2, which is a subset of V, and it'll be W2 valued, right? So then we can naturally define F1 star F2 from the intersection of the domains, right? Where both formulas make sense, and it will be W3 valued by F1 star F2 of X equals to F1 of X star F2 of X. The question then is, can we prove a product rule at this level of notation? I think we can. I think we can. I think we can. So what would I do? It's pretty simple. I would look at F1 of, you know, let's say X plus H. I'm using X instead of P this time. Star F2 of, let me stick with, I've been doing P everything else. I'm going to stick with P. Fine, P plus H, right? Let me not change my notation all of a sudden. All right. Now those, of course, can be replaced with what? And this is F1 star F2 of P plus H, right? By definition. Which then, of course, is F1 of P plus the differential of at P of F1 H plus the error in F1 of H, right? Star F2 of P plus the differential at P of F2 of H plus the error function at F2 of H. All right. And then use the bilinearity of the product. So bilinearity of the product means that we've got F1 times F2, which I'm just going to write as F1 times F2 of P, right? Got that. And we also have plus, notice that we have, well, there's some things going on here.
Shouldn't we distribute the whole thing into each of those?
Well, I have a suspicion how things are going to go. I'm pretty sure I should keep this, and this, and this, and that together. Let's see.
Combine all the others entire.
Yes, I believe so. I believe so. So this would be F1 of P times the differential at P of F2 of H plus the differential at P of F1 of H times F2 of P. That is my candidate for the differential at P of F1 times F2 of H. I believe we can argue that that's linear in H because the constants will filter through. We're assuming the assumed bilinearity of the star product becomes important there because I have to pull the constant through there to get it out front to like get the homogeneity that I need for the differential. But it is a straightforward exercise to prove that what I wrote in purple is in fact linear in H. And then what's left? Right, what's left? Well, oh man. Plus, looks like I've got F1 of P times A to F2 of H, right? Plus, oh, I guess I should have kept that, right? Let me write these together. F1 of P plus dP F1 of H star A to F2 of H, right? And then plus A to F1 of H times F2 of P plus dP F2 of H. I'm just writing this to be symmetric, right? And then of course there's also the A to F1 of H star A to F2 of H, right? Let me count. 1, 2, 3, 4, 5, 6, 7, 8. I'm missing something. Because if I got 3 things times 3 things, I should have 9 things. What am I missing? One, 2, 3, 4, 5, 6, 7, 8. Well, it's there. It's here. Oh, duh. Plus the differential at P of F1 of H times the differential of P of F2 of H, right? That's what I was missing. Okay, so then all this right here, right?
That's here.
That is our eta F1 star F2 of H, which we'd like to show goes to 0. But it's not just that going to 0 is not sufficient, right? We need to show that we have to demonstrate that you know, eta of F1 star F2 of H divided by norm H, right? That's the condition we found last time. That must be shown equal to 0 to get the to prove the differentiability of the product of F1 and F2, and hence the differential having this formula. All right, so some of this stuff we can handle pretty easily, right? Like as H goes to 0, this thing in brackets goes to F1 of P, so its limit exists, right? However, as H goes to 0 of, and so if we're dividing, so I probably, technically I need to, I proved a product rule for limits in here, didn't I? Yeah, we should use that now. So the limit as H goes to 0 of F1 of P plus eta, oh my bad, plus D dP F1 of H, that times eta F2 of H, right? Divided by norm of H. All right, so what's that equal to? That is equal to, literally equal to the limit as H goes to 0 of F1 of P plus dP F1 of H, all right, times the limit as H goes to 0 of eta F2 of H over norm of H, which is equal to F1 of P times 0, which is 0. And here I'm using, of course, the product rule for limits that we proved the other day for this Uber product. And so the same argument, notice that I'm pulling this, I'm using the bilinearity, the homogeneity, the fact that we can move constants from one part of the product to the other just to absorb it into the second part where it needs to be to get that this limit, the more delicate limit, is actually going to 0. And the same argument can be given for this one. And this one is easy because if we divide that by norm H, again by the product rule, we can do like eta F1 of H over norm H times, you know, eta F2 of H, right? And that's going to 0 times 0, which is 0. So that's that term, again, by the product rule for limits as H goes to 0. I think the one that, well, even the last one is, again, by the product rule, right? So this one, as H goes, oh, okay, this one's a little bit fussy. That is the one that's fussy. That's the one that's fussy. So we've got, if you follow my arguments, we've got this piece, we got this piece, we got this piece. These separately go to 0 upon division by norm H. But we still have to face, how is it that this goes to 0? And that actually involves an argument which we haven't come across yet. But it's an important argument in the story of multivariate analysis, and it'll come up again as we face certain more delicate questions. So how should we handle that? Maybe I won't even, maybe I'm maybe I'll resist the urge to use my limit laws there. I guess I could. But here's the question. Why is the limit as h goes to 0 of the differential at p of f1 of h, right, times the differential at p of f2 of h divided by norm h, right? We'd like to understand why this is 0. So I mean, we can replace this with like the limit as h goes to 0 of dp f1 of h over norm h, right? Times the limit as h goes to 0 of dp f2 of h, right? And, okay, well, this is 0, so this would be equal to 0 if we can show this limit exists, right? So if this limit exists, then the product rule fixes it for us. So really, we just need to prove that the limit of this is 0.
Why is the second one 0?
Oh, because we proved continuity of a linear map last time, and so this is literally equal to dpf. Once you ask, I have to finish. I know, but yeah.
But then why do we need the other one?
Oh, it's not obvious that that's 0.
Yeah.
It's not obvious yet. It's not obvious. Oh man, I forgot the camera. It's not obvious that that's 0 yet. Not at all obvious. So like.
As long as one of the two is 0. As long as one of the two is 0.
Oh, well, that's not enough. You need the other limit exists to use the product rule for limit. Product rule for limits assume that they both exist. If one of the limits doesn't exist, then you got to resort to a squeeze theory, like a squeeze theorem argument or something like that. Now, in our current notation, it's very cumbersome. So we should prove a lemma. Lemma. If T is a mapping from V to W is linear, then the limit as h goes to 0 of T of h divided by norm h exists. I sure hope this is true. If this is not true, then I'm in trouble. I'm actually not 100% sure this is true, Ernesto. Like I'm pretty sure this is true. But it's been a few years since I taught this, and I'm a little worried. All right. What are we up against here? So at this point, I need to like face the epsilonics, if you will, right? Like proof. Let's say V is equal to the. There may be a way to do this without resorting to this kind of stuff, but I'm going to do it. V is the span of beta. All right, and beta is, as usual, V1, V2, Vn, right? And W is, as usual, the span of gamma, and my gamma is W1, Wm, right? I'm going to assume these are normalized bases to keep things, nice. And we have a formula, right? t of x we can write as the sum I equals 1 to n, sum j equals 1 to m of a j I x I w j, where x, of course, is the sum I equals 1 to n of x sub I v sub I. That's a formula for t since it's linear. We're trying to understand, so maybe this limit doesn't exist. I'm not sure this exists. I mean, let me just drop down. So, you know, sometimes you got to know when you're beat, right? So in Rn, we just have T of H is equal to AH, right? The matrix times H, the matrix column product. And so when I look at like T of H over norm H, what I'm up against there is equal to A times, you know, H over norm H, which is equal to A U hat. And there's really no reason, this has to be same, you know, same for all U hat. However, it is true that the norm, right, of this is, you know, equal to, like, well, it would be nice if it was equal to the norm of A, wouldn't it? I'll put some quotes on that right now because I don't think that, I mean, I haven't justified that step by any means, but my point to you is, like, if you think about this, if you just look at this like heuristically, if I'm finding a bound on this, I'm bounding that. Well, U hat's this is a unit vector, right, for H not equal to 0. So that's length 1. So just basically however big A is how big this quotient can be, which means that we're taking the limit, when we take this limit, we're taking the limit of something that's, well, so this is too greedy. It doesn't exist necessarily. Too greedy. Nope, we have to replace that with, you know, if we look at T of H over the norm of H, right? The norm of that is less than or equal to M. So in other words, this is bounded. So because that's bounded, and because this goes to 0, we're able to prove that the product exists. So we can't use the product, so we actually can't use the product of the limit theorem on this piece. We need a separate argument, which is more nuanced, to prove that this product, maybe it's less nuanced actually, I don't know, but obviously we have to face this directly. All right, so let me fuss with this for a second here. So I'll stick with this claim. I like my formula. Okay, I like my formula. Let's keep the formula. Let's erase what's in blue, and let's see if we can't do that. Do you need to take a picture, or? Yeah. So if we take, and I guess we're looking at t of h, right? So let me change the letter on us here. That's h, right? H, there we go. H, H. So this has what? This has the absolute value of h sub I, right, is less than or equal to the norm of h for all I. We have that. And so if we divide this, if we look at t of h divided by the norm of h, and we take the norm of that, what on earth is going out there? Somebody felt like they were about knocking down my wall earlier, and well, the thing is, we're looking at the norm of, you know, the sum. I'm just going to put I and j and not write it out, but you got yourself an AJI, right? You got HI over the norm of h. I can bring that there, right? And then you got your WJ here, right? Now that is less than or equal to the sum, IJ, of the absolute value of AJI, right? And then times the norm of HI over well, this is, I don't even know, this is just a number. Absolute value on that guy, all right? Okay? And then we got norm of WJ. This is the triangle inequality. Now this is at most 1. So this is less than or equal to the sum over I comma j of the norm of the absolute value of AJI. And if we assume that this is 1, if we normalized our basis, then that's gone. This is at most 1, so we get that, right? And we can just let this be like, so that's less than or equal to, like, we can just do m times n times the maximum of, you know, these guys. And that can be our big M. This is really close to the thing we were doing the other day with the product rule almost, right? Like there is something more to say here. If I had all my ducks in a row, I'd say it right now. We eventually define the norm of an operator. Like an operator, the norm of an operator is defined to be the supremum of t of x, the norm of that, such that the norm of x is equal to 1. So basically you define the norm of an operator by the supremum of its values on the unit ball. And if you do that correctly, you can make that the M. I mean, you can almost see that from here, because this, if you look at it, is what? It's the norm, right? Of t of what? Of h over norm h, right? So what we're looking at here really is the linear transformation on the unit ball. So if you define t, the norm of t, to be the supremum of the values, the norm of the inputs, basically, if you want, I could put a x hat here, but basically the norm of the values of the transformation on the unit vectors. If this is defined to be t, it's almost a tautology that, the norm of t of h over norm of h, right, is less than or equal to this.